But yeah, so today I'm going to be talking about, obviously what we've kind of titled here is Freenotypes, and it's extracting added value from routine milk recording using deep learning. So I think I'm going to be got an uphill struggle now after Tom's talk, but hopefully I'll give some interesting points and maybe show that we can use some of these methods to again hopefully try and develop further tools that can be of use to, in our case, to farmers, but maybe applicable to many different fields. So again, this isn't it's a group effort. It's work that's led by myself and at a time Werner Brand, although Werner's now left SRUC. So I can sort of take on some of his work, and I'm going to go over a couple of examples where we've used this methodology. So again, it's thanks to Francis for giving a nice introduction to actually routine milk recording in dairy cows already. So I won't spend too much time on these slides. But it's basically an internationally practiced method using mid-infrared spectroscopy, where we can take a routinely collected milk sample and predict milk composition. And as Francis already said, this is then useful for farmers for making informed management decisions. And again, following up from what Tom mentioned, that these kind of infrared methods, they're low cost, they're fast, and in our case, when we're working with animals, they're completely non-invasive. So these are milk samples that are being collected from the cow already, and we can take off something like 30 milliliters of milk, and then we can then put that through the mid-infrared spectrophotometer and get these kind of predictions. So I guess the kind of workflow is that an individual routine milk sample is collected from each animal in the herd. It's then analysed by mere spectroscopy, and then information, as I said, such as fat, protein, lactose, somatic cell count are then reported to the farmer, and the farmer could then use that information to manage the herd. But at the same time, if we collect reference phenotypes and retain the mid-infrared spectral data that comes off the spectrometers, we can then use that information to calibrate prediction equations to then predict these phenotypes. And again, in dairy cows and like I guess most of our fields, we're looking at phenotypes that are either expensive to record or are difficult to record. And this was shown back in 2011 by Sawyer et al. When they looked to predict individual fatty acids using this method, and also in the same year by McParland et al. When they were looking at energy balance. And then these studies kind of then raised the question of what other sort of physiological or biochemical signatures can we detect in the milk-mere spectra that's going on in the dairy cow. So just briefly, this review by DeMarchi et al. In 2014 kind of showed the popularity of these type of studies. So we could sort of see an increase in studies that are basically using mid-infrared spectroscopy to predict phenotypes from the milk. And I had a little look to check that this kind of trend was continuing. And we can see there's a lot of papers being published in this area. So what we're talking about is phenotype prediction. So we've been working with National Milk Records, our partners, for many years now. But what it allows us to do is repurpose existing data as well as use data that comes in each day. So this is to give an idea of the data that we're currently storing. So we've got records going as far back to 2013. And around the middle of 2014 is when we started basically retaining absolutely everything we could. Around 2018 is when the Edinburgh Genetic Evaluation Services, as a team within within SRUC, that's run by Professor Mike Coffey, got interested in using machine learning and deep learning. And then it's kind of sort of taken off from there. And just put in here that there's been a slight, we lost some, I guess, data, the data stream was interrupted because of COVID-19. But we're now seeing now that the country's starting to open back up, the data streams are returning to normal. So as I said, we've got data going back to 2013, and we can use that data to create new tools for farmers. So again, we're kind of calling these phenotypes because it's new phenotypes that we can predict using data that we actually already have. So we don't have to spend any kind of money collecting anything. All we're really doing is basically spending the money to maintain the servers that we store all this information. We've got, I guess, examples of successes where we worked on an energy balance tool. So I guess building on the information from the McParland paper in 2011, and again working with NMR to produce this energy balance prediction tool that is now available to their customers, which was published in the Journal of Data Science a couple of years back, using the PLS method. So this was the using the method that Tom was already talking about and that we all know. One of the issues that we started having when we were starting to look at, I guess, classification, categorical traits, binary traits, was we were finding it a bit difficult to try and get meaningful results. And that's when we started to think, we started looking into machine learning and deep learning, and we thought, can we predict? Can we use deep learning as a method for prediction? So again, we still run the PLS models for traits that we already predict, but for some of these other traits that we're finding a little more complicated, can we use deep learning? So just for anyone that isn't aware, so deep learning is a subset of machine learning, and it's basically a sort of simplified simulation of the brain, using artificial neural networks to then help to help us make better decisions. And one of the positives is that as you can see in this graph, over older algorithms, is that as we collect more data, we actually see an increase in performance using deep learning methods. And this was a famous plot that was from Andrew NG in 2015. And it means, I guess, we're storing a lot more data now. So we're starting to think that this could have been potentially the way forward for us. And again, I don't probably have to tell anybody this, but examples of deep learning seen in everything. I mean, pretty much every field that you can think of, from doing banking to driverless cars to doing Netflix recommendations, it's kind of all built on deep learning and artificial intelligence. But in agriculture, it has actually been quite slow. So I think we were at an AI conference, and our talk was really the only talk that was talking about applying this to agriculture. I think there was maybe like a driverless sort of combine harvester, but that was the sort of takeaway we took. So I guess the methodology of learning is that the network consists of many different layers. We have our input layer, which we call features. So in our case, this would be our spectral waypoints, and our output layer, which we call our labels. And this would be our phenotype of interest. And in between these two layers, we have what are called hidden layers, and there can be n number of hidden layers depending on the type of network we're training. And each nodes within all these layers are all interconnected, and we call this dense. So if we look at just sort of a link between two layers, if we look at the nodes, then basically what happens between each node is we assign a weight and a bias, and then apply some kind of activation function to the result. We then repeat this for all nodes in the layer until we get to the output layer. This is then validated internally, so you can think of it like a sort of cross-validation against the prediction equation that's just been developed by the model. We then apply an optimizer to calibrate these weights and biases, and then this gets repeated for a number of what we call epochs. So it's basically one one loop of the data set, so the training data. So I've mentioned we've got dense layers, and we can use these as classifiers, and they always end in an output, can end in an output layer, and they can start with an input layer. Another important layer, and one that we use in this project, is a convolutional layer, and we basically use this for feature selection. And these end in dense layers, so these kind of sit between the first dense layer and your input layer. So convolutional neural networks are used to extract higher level features for subsequent training. So we can take our original features, for instance, in this example, say a bunch of binary features. We can run some kind of filter over the data, and then basically generate what we call a feature map. We can then run multiple different features over the same input data and generate, a bunch of these feature maps that we can then run some kind of pooling function over. So in this case, we've done a max pooling, which just takes out the maximum number in each of these 2x2 matrices. And again, we can run this same pooling technique over each of the feature maps. Once we then have our feature maps, we can then basically use these to create, in this case, a vector of integers. So you can kind of see in this example, we've gone from a matrix of zeros and ones to an integer, to a vector of integers. And basically these features now are now higher level than our original features. And like all, I guess this would be the same methodology as what we all use, but we take our data set and we then split into three subsets. A training and validation set, which is used to train up the neural network and calibrate the model. and then a testing set that's never seen by the model during training, which is then the trained model is then applied to the test set, so we can get some kind of idea of how this model would operate out in the field. So we've got some requirements, and again, these are requirements for deep learning, but are applicable to probably any kind of database task. And we need clean training data. So basically, we need our features to be clean, and we need our labels to be definite. And we also need the data labels to be equally distributed. And we've also got to watch out for things like overfitting. But one of the, I guess, the really main things with deep learning is we need a large amount of data. So we've got, like I say, data going back to 2013. So we thought that was a good, I guess, repository of data to start looking at into deep learning. So for this project, we were lucky enough to be able to afford to buy an NGX station, so an NVIDIA DGX station to carry out the calculations. And the main thing that this computer has is 4 high-powered GPUs. So it's the GPUs that allow us to carry out these deep learning tasks over a CPU. And this basically runs out a Linux OS. And this is just off the NVIDIA website we found it's quite true that when we're using our laptops in the office to try and run these models, the laptop would be unusable. We couldn't, if a model was running, whereas the DGX station allowed us to run these kind of models, train up these models in a matter of weeks. And as we then got, I guess, better at carrying out these types of analysis, then we managed to bring that down to days. And so just briefly, you probably not need to know too much of this, but all our data is stored in SQL servers, and it's Python's the language we choose to program in this. We've got many sort of deep learning libraries already available to us. And everything's been containerized using Docker. So this is an important thing for, I guess, working with NMR. So once we've developed a tool, it's easy to pass them all the underlying code in a container and an image, that's just going to basically work off the bat. And the last thing I wanted to mention on the deep learning side is something called transfer learning. So when we were at this AI conference in 2019, we learned about this technique, which again we hadn't heard of before because we weren't computer scientists or data science, anything like that. But basically, it allows you to take a pre-trained model and then basically retrain that model for your uses. And it's used a lot in things like computer vision and natural language processing. So first example is looking at bovine tuberculosis. So basically, this is a zoonotic disease that's endemic in the UK and also distributed worldwide. It's chronic, it's slowly progressive, and it's a significant challenge it's a significant challenge in the UK cattle sector, but basically wherever it's found. So DEFRA lists this as one of the most important livestock diseases of cattle, and it kind of costs it's got an annual cost of around about 175 million, and this is through things like compensation to farmers, culling, doing control of badgers, all that kind of stuff. So it costs a lot of money, but there's also unseen impacts. So I mean, if you're a farm and TB is then found, there's unseen, so I guess like doing mental health and stress impacts on the farming families having TB and not being able to bring in animals or sell animals, and basically you're kind of sort of just stuck in time. So when TB is first discovered in a herd, then the herd goes under something called restriction, and we call them breakdowns. And during a breakdown, as I've said, no new animals can come into the herd, and no animals within the herd can then leave unless they're being slaughtered. Animals are then subjected to routine skin testing every 60 days. If an animal fails the skin test, it's then removed. So we call these reactors. If it passes the skin test, we call these non-reactors, and then they're basically skin tested again 60 days time. This is then repeated until we have 2 subsequent tests that result in no reactors. So once that condition's met, then the breakdown can then be sort of signed off. But unfortunately, so the skin test is highly specific. So if it reports that an animal has failed, then we can sort of be quite positive that the animal does have TB. But it's not as sensitive, which kind of means that there's a lot of false negatives, which means that animals that pass the skin test that do have TB are then free just to, within those 60 days, infect other animals in the herd. And basically this is why breakdowns can last doing anything from months and months to years. I think there's one of the longest breakdowns is something like 12 years long, because it just basically the test isn't picking up these false negative animals. So our objective was, during those 60 days, we could hopefully, in a dairy herd, we'd be getting routine milk recording data. So that would be happening every 30 days. So we've got the potential to get 2 mid-infrared spectral recordings during that time. And basically what we'd hope to do is to catch these false negatives earlier and get them either removed or quarantined until the next test, where they can then be tested with the skin test. And again, the workflow would follow the same as before. Apart from now, we're hoping that we've actually removed these animals slightly earlier, which means that the breakdown can actually end earlier. So then the farm can get back to working again and earning money. So basically, yeah, this is a little graphic showing that we can then hopefully, the objective is to alert this animal so that the animal can then be quarantined. So for this, we're working, as I said earlier, with our sort of long-term collaborators, National Milk Records, and we have access to all their herds. So this gives us, I guess, a lot of information on a lot of cows. Just for I guess for information, the NMR processed the 97% of the UK farms daily bulk milk. So that's the population level that happens every single day. On the monthly routine side, the data that we're working with, we're looking at more 60% of all UK cows. And again, so that's a lot of data that we have available to us. And what's really important is a lot of these animals are actually in the high TB areas in sort of Wales and England. Also worth mentioning is that all our data are standardized. So as part of a European project, Optimir, this standardization procedure was developed by Grillette et al. Is what the reference there. And this basically accounts for drift across the different instruments across time. And basically it means that what we can do is that any sort of spectrometers that are within that dairy network that are standardized, then these tools should be applicable and be able to be used. They use the data from those machines. So as far as the TB data goes, we have access to the Animal and Plant Health Agency's breakdown database. So this is all TB data for all animals in the UK. So this does include the beef animals, but obviously we're only interested in the dairy animals in this in this sense. But we basically have access to all the historic data going back even pre-2013. But again, we only have spectral data going as far back as 2013. So from 2013 onwards. Also worth noting that we're only using historical data due to legal reasons. We can't be making predictions on current data. So we're only using predictions on animals that we know have been slaughtered. And we also have access to the British Cattle Movement Service database, which gives us a lot of historic data on all animals within Britain. So again, we can follow these animals from wherever they go, whether it's from the date they're born to when they go off to slaughter. So one of the main issues is phenotype definition, and that's getting a really clean phenotype, so our label to start with. So basically what we wanted to do was select our responders because we know they have failed the skin test. But there's the issue that we don't know when they actually have TB. So we need a clean non-responder as well. So what we do is we take the responders and only retain their data. Then we would start at the test that they fail the skin test, and then go back in time, collecting all their subsequent data, all their preceding data, and try and find a test that we can be sure that the animal couldn't have had TB for that long and either not been seen or not started seeing the effects of it. And we call these grey area cows. So again, these are the cows that are more likely to give false negative results. So as I said before, they pass the skin test, but they actually are infected with TB. So what we do is we remove these from the data set and retain them for using later. And this gave us somewhere between a 6 and 8 month time period between what we're calling our accurate phenotypes of positive and negative. But also what this meant was that it doesn't depend on the definition of a non-responder. So within the UK, the different countries all have a different definition how they actually define a responder. So whether you're in Scotland, Northern Ireland, Wales, or England, it's different. So by doing it this way, we feel that we've kind of sort of taken that reliance out. And then basically what we want to then do is, after we've trained a robust model, we can then go back and then have a look at these grey cows. So then, yeah, all it was left to do was to then match our phenotypes to sort of concurrent spectral records. And again, this is kind of, yeah, we need to try and get as much records as we can. So the number of days I think we settled on was something like 10 days, plus or minus a TB test. So this gives an idea of the training data set. So because TB is a low incidence rate, so it's only something like 7%, we had a lot of non-responders, and then there was a lot of grey cows, but not as many responders. So this was kind of meant that we didn't have actually a whole lot of data to play with, even though we have access to all the TB data. So one of the things that we wanted to do was to see, yeah, we need a balanced model so we could undersample the non-responders, but again, it means we'd be having an even smaller data set. So what we thought we'd do was we'd use this synthetic minority oversampling technique and try and synthesize new data. And the way that basically worked was we run kind of like a k-nearest neighbors approach to generate new data, but as you can see on the right hand side, only within the body of the available data. But this meant that we had more more data to use in our models. And the really important thing here to note was that the synthesized data was only ever used in the training data set. It could never be used in the validation set, because we want to make sure that when we're validating against only real data. And this meant we could push up the data set, as you can see here, up to just under 16,000 records. Another thing we did, because we were to use transfer learning and we were new into this kind of sort of deep learning space, what we took was the standardized spectral wavelengths, and then actually converted them into a grayscale image that you can see here on the left. And then these images were then fed into the network, and it meant that we could use sort of computer vision libraries that a lot of research has already gone into developing, and rather than us starting completely from scratch. So for this project, what we were using was a library called PyTorch, which I think is the one developed by Facebook. And our pre-trained model that we'd say to use was the DenseNet 161 model, which again, I think is one developed by Google using pretty much everything. So we basically want to use that as a start, and then retrain that model using spectral data. And yeah, in this case, we're only looking at a binary classification, so we're 0 and 1. And initially, what we do is we would train the model with the deep layers frozen initially. So that would be when we're recalibrating the DenseNet model, and then once we have once we've then basically shown that model our data, we then unfreeze the layers and then let the model run through with a small learning rate. And we also put in an early stopper. So basically, just like doing anything else, we don't want to overfit the model. So we want to ensure that after, I think we settled on 10 or 12 loops for the data. When we see no change in the validation loss, then the model would stop. So this was our first set of results using only the real data. And the metrics we've got here, so our accuracy and our validation loss. So validation loss is basically a loss function that we can use to give us an idea of how the model might work in real life. So when it's shown completely new data. But this is part of the actual training process. So you think back to that original data set subset flowchart. These are the two data sets that are passed into the model. So we've got our training and our validation set. And we want our accuracy between the statistic and everything. We want that to be as close to 1 as possible, but we want our validation loss to be as close to 0 as possible. And the validation loss can go from anything from 0 to plus infinity. So if it's huge, then the model is useless. So in this case, we got an accuracy of 71%. Validation loss, though, was still, 0.71 is quite high, so it wasn't doing great. And you can have a look at the confusion matrix here, and we can see that we were still getting a lot of false positives and false negatives. Once we added in the synthetic data, though, we've seen quite an increase in our accuracy. So we were now as high as 95%, but our validation loss was also brought quite a bit down. And again, looking at the confusion matrix, we see that we've actually minimized now the number of these false positives and negatives. So we kind of thought that this was, for our initial results, we were maybe onto something, and we wanted to basically continue on from there. So this is basically just a table to just compare the sort of metrics between the two different data sets, but also using our inference data set, so our test data set. So this is basically the unseen data that we saved at the very, very start that was never shown to the model. So we see we've got a slight decrease in our accuracy and our sensitivity and specificity, but Yeah, still nothing too drastic, but also our sensitivity was still higher than I guess what is the current sort of skin test sensitivity. So as you can see here from a paper by Della Domenech in 2006, that it can go from anything from 52 to 100, but on average is around about 80%. So we're kind of excited about this. This is kind of sort of first results, and yes, we wanted to then continue developing the model and training it up. So this was our current results in the TB on the TB area, and this is from from an inference data set. So this is from a data set that the model hadn't seen at all. We've managed to actually push up the accuracy and sensitivity and specificity up to 99%. But what's really important as well was that our validation loss is now down to 0.02. So the accuracy combined with that validation loss kind of gives us an idea of how this model might perform out in the field. And what we wanted to do was basically then go back to those grey area animals and see what the model thought of those. So basically what we've done is only took the ones first, actually animals that were labeled as a 1, and we tried the model on that. And as you can see, it was pretty good at picking out the positive animals. So I guess you can see here, so 7 out of the 250 it predicted wrongly. But on the cows that were predicted as 0, so these are the ones that would, again, contain those grey area animals that we can't confirm whether or not they did have TB, because all we can go by is the skin test. That we're almost at 50%. So it's now our sort of hypothesis that 148 in red actually contains a lot of animals that are spreaders of TB, that are in the herd, that are passing the skin test, and basically keeping the sort of disease rumbling on. So now is what to briefly touch on the second example, which is pregnancy status, which was one that was being led by Werner Brand before he moved on to new pastures, and is now fallen to me to take over. So again, the trait is actually really similar to TB, and it's actually, when we first looked at trying to predict TB, we found it really difficult, and we didn't know what we were doing. So we thought we'd go and have a look at a trait that is maybe a little bit easier for us to try and analyze, and that was pregnancy. But again, it's similar. We're looking at a binary trait, something that is somewhat difficult to measure, but is of huge economic importance to farmers. So basically, when you want to find more, animals that lose their pregnancy is something that's really, really important. And that's kind of what we want to try and do. So you just sort of consider the standard sort of lactation of a dairy cow. Then we've only got a really small sort of time that's ideal for conception, and then we want to basically make sure that pregnancy is maintained. So it's kind of, we can hopefully use this type of methodology to monitor that. So again, we're using the mid-infrared spectral data, and this is basically a lot of the spectral records will be the same ones used in TB. So we can, as I said, we can keep on just repurposing this old data, changing the phenotype that we want to look at. And yeah, so basically, again, similar to TB, we have a time when the cow is pregnant, sorry, not pregnant, and a time when the cow is pregnant. And like the grey animals, there's this time in between where we don't know, we can't really infer whether these cows are pregnant or are not pregnant. So when we're defining our phenotype, we need to try and be as clear as possible, and to ensure that our non-pregnant cows are non-pregnant and our pregnant cows are pregnant. And again, we use the exact same methodology. So we use the same pipeline that developed for TB, or in this case, I suppose, developed actually for pregnancy, and that was applied to TB. And this was, the kind of initial results that we came to. So our accuracy during the validation part was, as you can see, 97%. So it looked quite high, and we got a nice low validation loss. But then when we applied it to our unseen data, so our inference, our test set, we got quite a drop. But I mean, 88% was still relatively high, and probably, I mean, a farmer would probably be quite happy to see a tool with that kind of accuracy. But what we did, we wanted to check it on data and give a couple of examples. So because we had information on services and when pregnancy and pregnancy losses were confirmed, we could then sort of feed that and have a look at some sort of case studies. So this is an example of the model for an animal, where we can see the probability of the cow's pregnant on the y-axis and the days in milk on the x. So we know when the cow was serviced. So you can see this cow was serviced twice, and then was confirmed pregnant just around about 100 days. And as we can see, the model then sort of maintains a high accuracy, a high probability of the cow being pregnant at that time. A similar example where we actually have a pregnancy loss, we can see that the animal was serviced 3 times and then was confirmed pregnant. And the model kind of sort of looks like to be following that, what was going on there. The model then sees a massive dip, and then actually coincided with a confirmed pregnancy loss. And the animal was then serviced again, so twice. So I guess the day that, or a couple of days after the loss was confirmed, and then again some days after, and then confirmation of pregnancy then happened just around about maybe 260 days. And again, we kind of see the higher probability of the cow's pregnant, actually probably from that first insemination after the loss rather than the second one. So it kind of led us to think that we can maybe use this tool for correcting inaccurate pregnancy confirmations, and looking at some maybe the unreliable pregnancies predictions that are late in lactation. And as we've seen in that previous example, that an animal becoming pregnant from a previous insemination could potentially be highlighted. So the next thing we wanted to look at was, can we add in any kind of animal effect in some sort of granularity? So as you can see, this is a cow. It's a picture of a cat. But when you think of this picture of a cat, it's actually made up of 3 different channels: a red, a blue, and a green. And we thought, well, can we apply that same kind of methodology for spectral data? But we'd only use 2 channels, so we'd only be using the red and green rather than the red, green, and the blue. But why would we do that, and what are they? So what we thought we would do is we take our data here. So we've got our labeled data. So on a spectral recording date, a milk recording date, whether the animal was pregnant or not pregnant. And then we combined those data. So basically now what we've got is a previous date and our current date. And then we're leaving from a previous state to a current state. So we've got 4 labels. So instead of binary, so 0, 1, we're now basically going from 0 to 3. So we can we know from the second label whether the cow has remained pregnant, or whether she's either lost a pregnancy or gone from a non-pregnant state to a pregnant state. And also it means that we need 2 spectral records to make our prediction. So it kind of gives us a little sort of fallback there, that if we've only got the 1 record, then we don't predict on that animal and we wait until we've got a previous and a current. And yeah, now it gives us sort of that extra data on the state of the animal, or the change in state of the animal. So the way that we worked that was basically just to run the data through, with the first 1060 waypoints being from the previous spectral record, and the second 1060 being from the current record. And as I said, we've now got this 2-part merged label, which goes from the first part being the previous state, and the second part of the label being the current state, and which is then just sort of encoded into 0 to 3. So basically what this did is that it gave us a validation accuracy of 88%, which was lower than the previous model when we were just using the 1 spectral record. But when we then carried out inference using this model, we've seen the same validation accuracy that actually was seen in the inference from the previous model. So even though the validation accuracy wasn't as high, the accuracy of the inference, so kind of showing this, applying it to new data, was a lot. Was the same. And what we found is that actually if we collapsed the prediction back to binary, so after prediction, we then actually seen an increase in accuracy of up to 94%. So that was something that was quite interesting, and something that we're looking more into now. So I guess I don't want to leave some time for questions, so I'll quickly just fly through these slides. But we've got, so our current proposed implementation, so we collect spectral data or sent to us on a daily basis, and we currently use that using the PLS method to predict things like fatty acids, energy balance, NEFADs, ketosis and things. And the deep learning model predictions would basically just fit into stage 2 here. When the spectral data standardized, we would then siphon it off to make our pregnancy and our TB predictions, and then our kind of traits that we decide to start looking into. Basically, at the moment, it just runs in a sort of command line pipeline, and the information that we get, that we've chose to produce, is information on the sample, and also our prediction, and then our confidence in that prediction. So, for instance, you can see a lot of them are 0.99, so the model is quite confident that it's a 1 or a 0. But in some cases, we get a low one. So for instance, in red here, we see that we're at 0.5. So the model couldn't make a decision on whether that was a 0 or a 1. So in this case, we wouldn't report that, or we'd ask for another spectral sample, to be analyzed. So yeah, that information could then be used to generate a report, as I guess currently would be done now, and then passed on to the farm. In instance, like for a phenotype like TB, where there's a lot of legal ramifications, where there's also DEFRA would have to be taken into consideration. And again, these are things that we're currently thinking about. So conclusions: predicting phenotypes via using sort of mid-infrared spectral data and deep learning looks to be promising. So we're currently now field trialing both the TB tool with DEFRA, and we're also field trialing the pregnancy tool with NMR. Sorry, NMR with both of them, but DEFRA's funding the TB trial. We've kind of also shown that synthesizing additional both clean and additional clean data, can boost accuracy. And again, we were limited by using SMOT, but there are actual deep learning methods that we can look to use to generate completely new data that doesn't rely on the underlying data, which again is something that we're currently looking into. We've sort of have a hypothesis that this could be used to identify these grey area animals, and potentially once it's been field trialed, we could then use the tool to then relabel these animals in the database, and then we'd have actually new data to continue with training. But yeah, we're currently carrying out further research to see if we can use the tool to sort of make some sort of suggestion at the point of infection, and also highlight the practicality to the dairy industry. On the pregnancy side, we feel that there is a signature for pregnancy in the milk that comes through into the spectral data. And yeah, one of the main points would be using it to improve profitability on the farms. So detecting losses a lot faster, so we can get a vet out there to confirm. So yeah, application. There's a lot of applications for these type of tools. In this case, the TB tool would allow farmers to be more engaged with TB testing in their herd, so they'd have a bit more ownership in it. And it also have ownership in, I guess, the monitoring health and general fertility of their herd. So as kind of showed this flowchart at the start of this kind of repurposing old data, creating new tools for farmers, but also we can use that information, as I've said, for herd management, health and fertility monitoring, and even looking at something like disease outbreaks. So we can look at other disease phenotypes, something like Iones, which again is a big issue in the UK and has links with TB also. But what we can also do in collaboration with eGenes at SIUC is that we can actually acquire new phenotypes for genetic evaluations, and then that data can then be used for genetic improvement. So it's kind of like a win-win, all using data that we already have available to us. So I just want to finish up on some take-home messages, which I guess probably don't have to say to many people here, but just the benefits of routine milk recording. So the more farms that are actually involved in routine milk recording just means that the more data we've got available to us, and hopefully the more tools that we can then help develop to help save money, run farms more efficiently, and things like that. But again, I guess it's always worth driving home that in the case of dairy cows, it's also non-invasive. So there's not kind of any kind of animal welfare issues there. And again, it's a fast and low cost. Wouldn't really, if you're already involved in routine milk recording, no additional work on behalf of the farmer. I can't finish one without mentioning this quote by Mike Coffey, that in the age of the genotype, the phenotype is king. And I think this is just as applicable to spectral data or any kind of big data set. It doesn't have to be genotypes. That once we've got all this data to work with, it's useless unless we have good quality, clean phenotypes, reference phenotypes to actually work with. This holds true pretty much in most of our data-based work. So finally, I just want to thank all our funders and data providers, and also the guys, technicians at NMR and also at SIUC. And if you want to know any more on this, I know I've kind of sort of flew through it quite quick, but both the pregnancy tool and TB tool have been published in the Journal of Dairy Science, and also myself and Meg's email addresses and Twitter handles are there. So any information at all after this workshop, then feel free to drop us an email. And finally, thanks for listening.
Thanks a million, Scott, for your presentation. It was really, really interesting. And we have 5 minutes before the break, and there are quite a lot of questions. I really wanted your talk because I had a question for you before starting with the others. We talked before about the problem of the sample size, so a number of observations in a data set. And do you think that synthesization of spectra can be useful also for regression purposes or when there is continuous traits?
Yeah, I mean, I think potentially it could. I think that definitely. So we found that smoke worked relatively well, but because we had that limitation that we could only use the data, the body of data available, meant that I guess we couldn't synthesize too much. So there was that kind of sort of trade-off. But I think using something like a GAN, so a generative adversarial network, so a type of machine, a deep learning method where you can actually create and synthesize new data from scratch, so just like from noise, is something that we're seriously wanting to look into, because then we can use that to generate not even just doing not spectral data, but any kind of data. So it's used a lot in the medical field for generate, or in the financial field for generating data that's, I guess, yeah, it needs to be kept secure. So you can't be looking at patient records, for instance, but you could generate data for doing fake patients that then can be used to train up the models. So I think that applying such a technique to generate more of that kind of clean data is something that could be looked into. And I'm not sure if someone's looked into doing that on I guess using more of the traditional methods or not. But I'd be keen to see if it would work just as well.
Thanks. I start with very starting question. So did you compare your models to more traditional machine learning techniques?
So we compared with PLS, because PLS was what we were using originally. So in the pregnancy model, there's a couple of pregnancy models using mid-infrared spectral data before we started looking into it. So one by Jenny Price's group, and we found that when we ran PLS on our data, we were getting kind of similar results to those ones in the literature. So yeah, but when we applied, I guess, the deep learning, we've seen quite an increase in accuracy. Again, but it could be down to a lot of things, not just the method, but even just the way that the phenotypes are derived. So ours were derived slightly differently. So yes, the only thing we've really compared with it to date is PLS. The TB model now. So what we're currently starting looking into is a method, a machine learning called XGBoost, which uses boosted decision trees. So that's what we're currently kind of looking into, following on from this work. And again, we're seeing high accuracies. And one of the positives of that is that we don't have to use the sort of the computer vision technique. So we don't have to convert the images to the spectra to images, but you can just run the sort of the standardized data into that model. So that's kind of where we're currently at.
Yes. And this question from Georgiana. So do you consider the data as tabular, independent input features, or as time series convolution filters to capture short and long-term dependencies of the input feature? Have you compared to other time series classification techniques, especially recent ones such as Rocket?
No, so I think we'd probably consider it tabular. So even though we're making predictions in time now, initially it was just a case of having a massive matrix of spectral data and corresponding labels. So yeah, on the time series side, we've not really looked into much else. I'd say we're kind of we're quite new to the deep learning way of doing it. I mean, I guess we've also been involved in a lot of the projects using, I guess, the more traditional methods. So it's something that we could definitely look into.
Thanks. And we have time for the last question before the break. And there are, like, your talk was really interesting, so there are other questions in the chat. If you want to reply directly on the chat during the break or after when we start again. The last question from Claudia. In the BTB model validation, did you submit data of cows with other diseases than BTB? Also, you speak about the BTB as binary classification. Did you consider a one-class setup?
So was that a one-class
setup?
All right. Yeah. So we didn't consider any other disease at the time. So we were only looking at that skin test. So we didn't look to, I guess, check whether the animals had Johne's or mastitis or anything like that. But what we did have access to is, because we had the entire database of TB testing, we had access to the other tests that are used for TB. So I didn't have enough time to go into it, but it's in the paper that what we've basically done is we created what we call kind of sort of skin test plus, which is the majority of the data was based on the skin test, but then we also had information on where the animal was slaughtered, if there was lesions on the lungs, the culture status, and we kind of used, and then also the gamma interferon test results. So we kind of used all that information where it was available to determine whether it was a 0 or 1. So yes, so we only ever considered the binary, but I'd be keen to talk about the 1 class. Yeah, that's something I didn't even think about.